In this lecture we talk about direct limit. So we start with the directed set which has an order. So always you can think of it as natural numbers which comes equipped with the order, and then you have these sets which are indexed by the set I. So you can think of these sets as A0, A1, A2, A3 and so on. So this is a family of objects indexed by some index set I. And then you have a morphism Fij going from I to j if I is less than equal to j. So this morphism satisfies the following conditions. So first is Fii, this is just the identity on Ai. So map from Ai to Ai, which will be given by Fii because I is less than equal to I. This is just the ID map. And then you have a natural compatibility condition. So I is less than j, so you put an arrow like this. J is less than k, so you have an order like this. This order is coming from this directed set. Corresponding to this order you have your index sets, and you have these maps. So this map is Fij, this map is Fjk, and this map would be F first index and then the second index. And this is precisely what is written here. So you first apply Fij right here, then you apply Fjk right here. You compose these two is equal to composing from here to here, that is Fik. So that is it. So then this pair, obviously all these sets indexed by I and mapped like this, is called a direct system over I. So once you have a direct system whose definition is just natural as we just saw, then you can talk about a direct limit. So the direct limit, which we will denote as A of the direct system, this is given like this. So written like this, and we are denoting this entire thing by A. This is nothing but disjoint union of all these sets modulo an equivalence relation. So what is this equivalence relation? So you pick up xi in Ai and xj in Aj. So they lie in the same equivalence class. So they are equivalent to each other. They lie in the same equivalence class. If there is some bigger index k such that Fik, so something like this Fik acting on xi is equal to Fjk acting on xj. So eventually there is some map which will make these two equal. So this will become more clear as we see some examples. So each element is sent to its equivalence class via the canonical function phi I this. So you can have, again, this is a disjoint union modulo some equivalence relation. So you can, from Ai, you can inject into A corresponding to your equivalence class. So the slogan which one needs to remember for direct limit for using them is that two elements in this disjoint union are equivalent if and only if they eventually become equal. So these are large number of elements. As you can see, this is a huge set because it's a disjoint union, and you say that two elements are equal when they eventually become equal under some mapping like this Fik Fjk. So we will give an example pretty soon which will make this clear. So direct limits are linked to inverse limits via this map. So you have home, you take the direct limit here, and when you take this out, this becomes inverse limit. So this is just remembering the fact that this home functor, this is contravariant. So the most important example for algebraic geometry is the stock of a sheaf. So say this F is a sheaf on a topological space X, then the stock at a point is defined as a direct limit over these sets U. So first, what is the index set? So index set is just these sets U which contain P. So this set point P is contained within some set U. And now you have to have a directed system. So this is just the inclusion of sets. So this set U will contain some other set, say U prime, which will further contain another set, and so on. So you take a direct limit over all these neighborhoods of point P, and you eventually get a stock. So the direct limit is being taken over open neighborhoods of P. So we can also talk about a germ of a section. So there might be the case that there are two different neighborhoods and they are not contained within each other. So say for example there is another thing like this V. So then we can talk about germs at point P. Obviously then you have to talk about intersection of U and V, and then you take sets which are contained both within V and U. So you need to talk about the set W now here, which is contained within both V and U. So the germ Fp of a section F in F of U at a point P which lies within this set U, which is contained within our topological space X. So this germ consists of this data U comma F, and it has to satisfy an equivalence relation, just like this equivalence relation here. You have an equivalence relation here. So this equivalence relation means that if and only if there is some open set W, just as the one I drew around P, which is contained in both V and U. Now P will lie in W such that this F when restricted to W is same as this G restricted to W. So you have this function which lives on this set V, and then you have another function which lives on this bigger set U, and you want to glue them together in the neighborhood of this point P, and that's what the gluing means. So these two functions might be different, but as they get closer in the neighborhood they become equal to each other. So just like, so say we have two functions. One function is like this in the neighborhood of 0. So this function is different from say another function which is in blue, but they agree in the neighborhood of 0. So you can glue them in this small cylindrical neighborhood, and that is the equivalence relation. So such that F in this neighborhood is equal to G of W. So the stock of a sheaf at a point P is a set of germs of sections at P. So just these germs. So if this sheaf F is a sheaf of rings, then the stock will also be a ring. So then again you can add and multiply these germs just like you would do in a ring. So by adding or multiplying the functions F and G on U intersection V. So again you have these two big sets U and V, and then you talk about this point P which lies in both the sets. Then you have to consider a neighborhood which is this shaded neighborhood W, and then you glue the functions here. So another important property of direct limit is that if you have index sets like this, this Li is AI module, Mi is also AI module, and then you have a system, a direct system like this, then you can take this direct limit over Li, over AI, and over Mi. Now this is important because this is used in the tensor product of sheaves. So when you're taking tensor product of sheaves, this relationship helps us give tensor product of stocks, and this thing here is tensor of stocks. So again the slogan is that eventually in some small neighborhood you are able to glue things together to get a ring here, and that is what direct limit would mean. So another example which is very important is, so for a prime P you consider the sequence. So this is just homomorphism. So this is just multiplication by P map, this is multiplication by P map, multiplication by P map, and so on. Now the direct limit would be Z1 over P. So a few words here. First of all, direct limit has the universal property. So if you want to show this is Z1 over P, you obviously have this natural injection. So you can talk about this phi I. So all of them are natural. What are this map Fij? This is just P to the power of j minus I. So for example, you want to talk about map F22 from here to here, it has to be identity map, right? So 2 minus 2 P to the power of 0. If you are going from here position 2 to position 4, then you are multiplying by P square, which is exactly 4 minus 2. If you are going to position 5, from here you have to multiply by P5 minus 2, which is P cubed. So you need some inspiration to come to here, and in order to prove that this is the direct limit you have to use the universal property. So I will not go into the proof of this, but you can just start with some set X and call it the direct limit, and then you have to construct map from Z1 over P to here, and then say that satisfies the universal property, so the z1 over p is the direct limit. Now this is an important construction because you can think of each map of degree p in topology is induced from the map of spheres. So map of spheres, if descended down to homology of spheres, you will have map z to z on the homology of the sphere. So you can say HNSN to HNSN, so the nth homology group of spheres. So this you are saying is degree p. So now you multiply by p, you can get a direct limit of z1 over p. So you can view z1 over p as a degree. So elements of z1 over p are degree maps. So naturally the question arises, how do you transport this information to other areas? For example, algebraic geometry, how do you talk about degree z1 over p? So for that you need the notion of perfectoid space. And this is a very active area of research right now.